Okay, we were solving this problem. Um, uh, Actually, we stated the problem, then I said that I'm going to solve it. So solution is very simple, no problem with this, but the physics is important. So as a result, let me actually erase some of the details in here. So the area is just 1/2 and the separation is d. Um, So in any case, so we can actually attack the problem in the same way, but I'm going to start with questioning the assumptions. So I'll start with this. Uh, so the question is, does the charge on the plates, does the charge, is the charge, distributed uniformly over the surface, over the plates? Okay. So do we have a uniform charge distribution in here? And if you just look at the problem, it doesn't have to be so. So it is possible that, for example, in this region, the charge density is, the surface charge density might be, I don't know, a little bit larger perhaps, or a little bit smaller than the charge density in here. So you can see that the charges on that part of the surface, are seeing a different physical environment in here. They don't see any dielectric material in here. They see a vacuum. So as a result, the charges in here see a different medium. And because of that, it is possible that the charge densities in these two parts can be different. So this is the first observation. So that's sigma 1, let's say. And let's say that the charge density in here is equal to sigma 2. I don't know if they are equal or not, but there is no way that, I mean, there is no extra information that will enable me to conclude that they have the same density. I don't have any such information in here. So in any case, but since, again, this is an exaggerated picture, so this area is large, these are very close to each other, so therefore the opposing sides of the capacitor should have the same density, because somehow there should be somewhat a local neutrality of the charges. So that's minus sigma 1. So the answer is no. Okay. The second thing, so the electric field. So the electric field inside the dielectric is equal to E1. And the electric field in the vacuum is equal to E2, let's say. So the question is, do E1 and E2 are E1 and E2 equal to each other? Probably there's no reason for that. Well, it appears that there's a reason, actually. The reason is that basically, I mean, this whole plate is an equipotential surface. So they are at the same potential. And so this whole plate too is an equipotential surface. So if you just compute the potential difference, let's say, between these 2 points and between these 2 points, so between these 2 points, you have to go over this path. Between these 2 points, you have to go over this path. But eventually, you need to compute the same potential difference. So that potential difference is equal to E1 times D. But the same potential difference should be equal to E2 times D. So these are the same. So that would then imply that E1 is equal to E2. Okay. So it appears that in that particular case, the electric fields are the same, but the surface charge densities are not, right? Because the geometry is different now. So in the previous case, we had a single surface charge density in the previous situation geometry. So that was a different thing. This is a different thing. So somehow, because of the fact that the the plates are at equipotentials, it appears that in this particular geometry, the electric field should be the same. Okay, so as a result, I cannot solve the problem in the way that we have designed the solution of the previous problem. I mean, I started with, say, like, let charge be on the place be equal to Q. Then let's compute the potential difference. I cannot do it like that. This is kind of difficult, but I can go back. I can assume the potential difference. As a result, this is the method in here, right? Let potential difference be V, and then find the charges on the capacitor plates. And then the capacitance would be a Q divided by V. So our starting point is different, actually. So we assume that the potential has a known value. From this value, we just compute the charge on the plates, and then from the ratio, we find capacitance. Okay, let's quickly do this. So all right, I think I'm going to do it like this, okay? This is a straight line now. This is a straight line, and I have a rectangle in here, right? So let's use the this thing. So okay, what I do is, well, first of all, I mean, I know the potential difference, so therefore, sorry, I know the potential difference, so V is known, and express everything in terms of these. So therefore, I can express the electric fields as V divided by the distance between them, the distance between the plates. So I now have an expression for the electric fields. Okay, so I know what the electric fields are. I need to find the surface charge densities in here. It's the sigma 2 in here and sigma 1 in here. Sigma 1. So to do this, I just choose a Gaussian surface in here. Okay, so I'm going to call this as S1, and I'm going to call the Gaussian surface in this one as S2. So I think I'm going to do this thing quickly. So I need to apply the Gauss law for both of these surfaces. So this is epsilon E dot dA. That's equal to the enclosed charge. And I think I'm going to use the same base area parameter, little a, for both of them. Okay. So for this surface, the flux is coming only from this surface. So the permittivity is equal to K times epsilon 0. Electric field is E1. Area is little a. And the enclosed charge is sigma 1 times little a. And I know what E1 is. So this is like K times epsilon 0. V divided by D is the first surface charge density. Okay. And then I apply the Gauss law for this surface. So let me write down the expression. On S2, we have epsilon 0 multiplied with the electric field dotted with the area. That's the enclosed charge. So in that case, we get, again, we get contribution coming from the right base. So therefore, this is epsilon 0 E2 times the area. That's enclosed charge is equal to sigma 2 times the area. Areas go away, and I know what E2 is. So that's epsilon 0 V divided by D is sigma 2. Okay. So, and I know that these surface charge densities have this, make up the whole charge. So the charge on the positive plate is therefore the total charge is in here plus the total charge in here. What did I do wrong? So this is sigma 1 multiplied with A over 2 plus sigma 2 multiplied with A over 2. And I do the calculation, the rest of the calculation. Sigma 1 is K epsilon 0, V over D, A over 2. This is epsilon 0 V over D A over 2. Did I forget anything? I don't know. So this is K plus 1 over 2 epsilon 0 A over D times V. I know that this has to be equal to the capacitance times V, so therefore the capacitance is equal to K plus 1 over 2 times epsilon 0 A over D. Okay. So again, check. K is equal to 1. What happens? Check what happens when K is equal to infinity, for example, and try to justify this by picturing the physics in there, okay? So as a result, let me quickly go over this. So there is this alternative method in here. So this is the alternative. So that's the circuit method. In that case, you basically think of this as two capacitors which are connected in parallel. And I know that in this situation, the capacitances are added up. So I'll think of this as this capacitor circuit, where each individual capacitor has an area A over 2. Okay. Yeah, whatever. I mean, you just do the calculation. So I'm not going to do it. So you can do it yourself. So there's a surprising third method. So that's the energy. Okay. So it basically goes on like this. So I can actually compute the energy. So think of it like this, right? I know that, well, the electric field in here is equal to E1, and which is equal to E2, but I'm just going to show it E1 and E2 again. Okay. In any case, so the question is this. So let's say it like this. So assume V is known. Compute total energy U of the capacitor. So I know that this total energy should be of the form of one half of C times V squared. And then from this expression, of course, you are going to obtain an expression where there's a V squared in here, and just read the coefficient and then find the capacitance value, right? That's the method in here. So how do I compute the total energy? Total energy is basically the integral of the energy density. Energy density, right? Multiplied with the volume in here. So in any case, since the electric field is uniform, the energy density is also uniform. So I can even I can compute this integral without doing any integration. I just need to multiply the energy density with the volume. But let's remember this energy density expression. So this is the little u that I'm writing down. So this little u had this formula actually. So that's 1/2 of epsilon 0 times E squared, but it contains an epsilon 0 inside. So in the new formulation, therefore, this energy density has to be equal to 1/2 of epsilon times E squared. Just remember the prescription that all the all the permittivities should be replaced with the permittivity of the medium. So if there's a medium, the energy density, therefore, should be computed by using the permittivity of the medium. Okay, so that's the only change in here. I didn't give this formula, but you can derive it in the same way, no problem. The way that we deduce the energy density can be applied to that situation as well. So you can easily show that, no problem again. So this prescription of replacing epsilon zeros with epsilons also applies in here. So I'm going to do it also in that case. However, just notice this, that the electric fields are the same in here, but the energy densities are different. So let me use a yellow color for that. So the energy density on that part, let me call this as U1. The energy density on that part, let me call this as U2. So I know that U1 is 1/2 of permittivity is K times epsilon 0 times E1 squared. I know what E1 is, so therefore this is K times epsilon 0 times potential difference squared divided by the distance squared, separation squared. Right, that's what the first energy density is. The second energy density is, well, basically the same thing without the K. So U2 is 1/2 of epsilon 0 times E2 squared. And so therefore this is 1/2 of K epsilon 0 times, sorry, there's no K, epsilon 0 times V squared over D squared. So the energy density on the dielectric on this part is actually bigger. Okay, so what's the total energy? So for the total energy, let me use a white color. So the total energy is equal to the energy density in the first part multiplied with this volume. So the volume is basically area times the separation. So that's basically the volume of the dielectric. And energy density in the second part multiplied with the volume again. So this is the volume of the vacuum. So let me write this thing down like this. So this is the volume of dielectric. This is the volume of vacuum. Right? That's the thing that I'm using in here. So as a result, the energy density. So let me write this thing down and see if I can collect everything. So we have 1/2 of K times epsilon 0 V squared over D squared multiplied with A over 2 times D in here. I have the same expression but without the dielectric constants in here. Okay. I can see that these cancel. I can see that, well, I'm going to keep the first 1/2 intact. And I'm going to use the second one as like this. So that's K plus 1 divided by 2 multiplied with epsilon 0 area divided by D times V squared. I know that this is of the form of 1/2 of C times V squared, and therefore I just read the coefficient. So therefore the capacitance is equal to that. Okay. So this is a third alternative way. I mean, in this problem, that doesn't appear to be too simple either. But there are some situations where these kind of alternative points of view is very useful. Especially in places where you're confused, actually. Okay. So I'm not going to solve this problem. So that's some other problem that I'm just going to illustrate some of the things that we have done. So suppose that this time the dielectric is not, well, it is both actually. So let me do it like this. So suppose that I have some kind of a dielectric material. This one is blue for some reason, and this one is purple. Let's say it like that. So I say this has a dielectric constant K1, and this one has a dielectric constant K2, K1 and K2, whatever. And I have vacuum in here. Okay. So in this case, I'm going to have, there's an electric field in here. Let me call this as E3. There's an electric field in here, E1. There's an electric field in here, E2. I know that E1 and E2 does not need to be equal. Well, they are different. Actually, by using a Gaussian surface in here, I was able to show that the ratio between these electric fields is the same as the ratios of the dielectric constants in one way or the other one. I don't know. So they are different. And so as a result, there is no reason that this electric field in here, this E3 is equal to either E1 or E2. They don't have to be. Moreover, the surface charge density in here will be probably larger than the surface charge density in here. So as a result, you can see that this is a slightly more complicated problem than the previous one. So if you want to solve it by using Gauss law, it's a little bit more difficult than the other ones. But you can use these kind of principles again. So there are 3 unknowns, but you can, for the electric fields, and 2 unknowns for the surface charge densities. You can see that, for example, if that distance is d, let's say, and that's d over 2. Let's say it like that. So E3 times d, so that's basically the potential difference between the places, equal to E1 times d over 2 plus E2 times d over 2. You can use these kind of principles to find some relationships between these quantities and then eliminate some of them and whatever. And then use Gauss law to relate these E1 to E2, and then, I don't know, just use some method to actually compute these kind of things. In any case, so as I said, I'm not going to solve it. There's no point of solving this problem in here. But these kind of problems, which are a little bit more complicated, are best attacked with these circuit equivalent capacitor formulations. So as a result, probably it is better not to go into this kind of a picture. But I just talked about this thing because I want you to be actually know about this picture in here, that the electric fields do not need to be the same, and similarly for the surface charge as these two. So as a result, this kind of a picture is important. Okay. I don't know if you have any questions. I think I'm going to go forward, and I promise that I need to do some discussion about this. So it is this situation, right? Okay, so that's the dielectric in here, that's the vacuum. Vacuum in here. And we have some charge in here. So let's say that the surface charge density is sigma minus sigma. And then we have deduced that the electric field in here is, within the dielectric is, this is the first problem that we have solved. It is sigma divided by k times epsilon 0. But the electric field within the vacuum is sigma divided by epsilon 0. So the essential idea, I think the important idea in here is that the presence of the dielectric makes the electric field weaker. Makes the electric field weaker. So vacuum is the worst dielectric in a way. So in that case, the electric field is the strongest. If you increase the dielectric constant, then the electric field produced inside would be smaller, assuming the same charges, same charge distribution, right? So as long as you have the same charges in place, but you're just changing the dielectric constant of some medium, in that case, within the medium, the value of the electric field will become smaller as K becomes larger. So we can see this clearly in this geometry, but for other geometries as well, like, for example, the electric field produced by a point charge. It's the Coulomb's law, essentially. Point charge inside the dielectric. This also gets weaker. And we would like to understand why this is the case. Okay, and I'll try to explain it actually. So the essential idea in here is this. Basically, there are some molecules in here, right, inside. So let me just think about it like this. So I'm just going to concentrate on a molecule in here. Okay. And what happens is that, so I have a molecule, so that's the, yeah, I just draw this as if this is an atom, but in any case, it doesn't matter. So we can easily talk about the molecules as well as the atom. So think about it as a single atom. So in that case, we have some kind of a positive nucleus, and then there are these electron clouds in the outside. So the question is, what happens if a molecule is placed inside an electric field? Okay, so there's some kind of an electric field in space in here. So I don't know, let me draw it like that. So it doesn't matter what it is. So it is from left to right. Right? In that case, I know that the positive charges are going to feel a force, the electric force, in the direction of the electric field, but the negative charges are going to feel a force in the opposite direction. Right? So it doesn't matter whether the electrons form a cloud, actually. That's not the relevant issue in here. But because of the electric field, there will be some kind of an external force applied on them. Okay, so because of that, there will be a displacement, right? So positive and negative charges displace in opposite directions. This displacement is actually very small for ordinary electric fields. Even for extremely large electric fields, we cannot get very large displacement. But I'm going to exaggerate in here, right? This is just the exaggerated picture. What happens is that, in such a case, that the protons go forward, electrons go backward. So as a result, there is some kind of a some unequal charge distribution inside the molecule or inside the atom. Okay, so this configuration basically looks like a dipole, where what happens is that I can imagine it like this. So there's a negative charge in here which is displaced towards the left side, and a positive charge which is displaced towards the right side. So therefore there is a dipole moment. Okay, so that means a dipole is produced. So therefore there is a dipole moment. Electric dipole moment, that is. So this is the dipole moment P. So that's basically the distance multiplied with charge, that's separation multiplied with charge. So what is important in here is that P is in the same direction as the electric field. Okay, so somehow I can actually express the interaction of a molecule with an external electric field like that. So if you apply an electric field to a molecule or an atom or whatever, it's going to polarize. So therefore it's going to develop a dipole moment. Right? That's kind of the simplest picture. So it appears that this is called the induced dipole moment. So that's the induced one, induced dipole moment. It is induced by the presence of the electric field. So it appears that this induced dipole moment is proportional to the electric field. It's not only parallel, but it's proportional for, at least for weak fields. So there's a constant of proportionality in here. This constant of proportionality, I think people show it with alpha, is called the polarizability. Of the molecule. High depolarizable molecule means that if you apply a small electric field, it just develops a large polarization. Okay. So this is for perhaps an explanation for a molecule which is not already polarized. But there are other molecules like, for example, water molecules. You know the water molecules? These are already polarized, so they have some kind of a permanent dipole moment. Right? So I don't know, there are these water molecules, for example, in space. You know these. I have talked about these because, so if you have applied electric field, this time what happens for these ones is that these are already polarized, so they don't develop any polarization. But what happens is that they actually rotate. Right? They rotate so that eventually they orient parallel to the electric field. So the dipole moments of the water is going to become parallel to the electric field. But of course, there's some kind of a randomness involved in here. I don't want to go into this part in here. So as a result, you should really be talking about the average dipole moment in here. So let's say it like this. So this is the P average. So that's the average of basically the dipole moments of all of the water molecules. This appears to be also proportional to the electric field. Okay, so as a result, you can also talk about the polarizability of the water medium this time. It's not the polarizability of a molecule, but the medium itself. And you have essentially the same kind of a thing, right? When you apply an electric field to water, it would also display a polarization in the same direction as the electric field. If you remember, I talked about this in this running water example. I said that if there's some kind of a faucet in here, water faucet, and then you bring in some charge, positive or negative, doesn't matter. You can attract this water towards the charge, if you remember. It was about this kind of an issue, right? Somehow the water molecules orient themselves parallel to the electric field and so on, whatever. In either case, what happens is that all of these molecules inside this medium develop a dipole moment, which is parallel to the electric field. So there are all of these molecules inside, and that somehow shows some kind of a response to the electric field by just developing a dipole moment. So it doesn't matter whether the molecules are like already polarized molecules like water molecules, or I don't know, the atoms like helium atom, which is not normally polarized, but it becomes polarized after the application of the electric field. So in all of these cases, all molecules react in the same way. So they develop a dipole moment parallel to the applied electric field. And some materials show strong reaction. They have a high polarizability, so therefore they have larger dielectric constants. Some of them have smaller polarizability, and so therefore smaller dielectric constants. So there's some kind of a relationship between the dielectric constant in here and the polarizability, but just know that they are proportional to each other. There are some unnecessary, geometric factors that have to be included in the relationship. So as a result, I'm not going to talk about this. So this is qualitatively. So the presence of the dielectric makes the molecules polarized, and somehow this makes the electric field weaker. And the question is why? This is the thing that I need to explain. Okay. So this is the point where I draw the second picture because I need to do this. Okay. Again, exaggerated picture in here. So I have this dielectric in here. I have a small molecule inside. I have some positive charges in here. Because of these positive charges, there's an electric field produced in here. I think I'm going to call that electric field as E2. So as a result, I'm going to explain this as some kind of events that happen with some kind of a time sequence, right? So first, all of these charges produce an electric field in here. Let me call this electric field as E2. It's the same electric field that would be produced in here, okay? So please don't get confused by this. So that electric field somehow polarizes this dipole in here, this molecule in here. So this molecule develops a dipole moment. Because of that, this molecule itself will contribute its own electric field. So therefore, it's going to produce an electric field lines in space. I'm just going to draw the electric field lines of that molecule only, all right? So I'm not going to draw the electric field lines of all the molecules, just that molecule only, all right? But actually, what happens is that we have the electric field produced by these plates, plus the electric field produced by this molecule, plus the electric field produced by all of the molecules. As a result, at every point, I need to add up the effect of all of these electric fields to find the total electric field, okay? And E1 is the total electric field that, that is produced, right? So there's a tricky bit in here. So let me just call it like this. So I think I'm going to write it down like that. So E1 is the total electric field produced by first charges on plates. So these are actually called free charges, and two dipole, all molecular dipoles, right? But I need to add them up. Unfortunately, each molecule produces an electric field in different directions. So for example, at this point, I'm going to show this with a yellow color, sorry about this. At this point, for example, this dipole creates an electric field which is parallel to the dipole moment. But at that point, it produces an electric field which is opposite to it. So as a result, mathematically, this problem is very complicated. Just computing this sum of the electric fields produced by all of these molecular dipoles. This is difficult, okay? So all I need to do is somehow, I need to solve this problem. Just take a point in here. I know that there's an electric field produced by the free charges at that point. I also know that all the dipoles produce an electric field in here. So, but these are all in different directions. But somehow I need to add them up. So when I add them up, it appears that the electric fields in the opposite direction somehow becomes dominant. So as a result, all of the electric fields produced by all dipoles appears to be in the opposite direction, okay? So at this point, I can just tell you the result. I cannot convince you that this has to be so, because this is a complicated problem. So let's say it like this. This is the induced electric field, basically, okay? So this is what I call as E induced. This is the induced electric field. So the electric field E1 is equal to the electric field produced by the charges on the plates plus the electric field produced by all the molecules. So these two are opposite to each other. So the induced electric field is opposite to the applied electric field. Okay. So because of that, the total electric field is weaker. So if you just take the vector sum of these two, this is now weaker, which means that E1 is less than in the applied electric field. And that is why in dielectric media, the electric field becomes weaker. Okay, so that's the explanation for this effect in here. So apart from saying that, there's some kind of a complicated mathematics in here, I cannot do any better than this. But I mean, this can be done, right? You can actually handle that mathematics. I don't know if you are going to do this in any course, but some of you may see this kind of a treatment is carried out in some certain textbooks. Probably not in your textbooks, but this is basically what should be done. And when you do this properly, you're going to see that this induced electric field is in the opposite direction. Unfortunately, this is not how people explain it in textbooks. So there's actually something called an induced charge explanation. They say that there are some charges that are collected at the surface of this dielectric slab and things like that. Don't believe in these kind of things. There are no such charges at on the dielectric. So the dielectric is always completely neutral. So every part of the dielectric is always neutral. It happens that you can solve this mathematical problem by actually solving a different problem where you kind of assume that some surface charges are collected. So this is actually some kind of a mathematical trick that people use, but it's a mathematical trick, right? Some people actually confuse the mathematics that you use with the physics. Sometimes to solve a physical problem, you solve a different physical problem with a different mathematics, and so for that reason, they just confuse the physics. This is an example of such kind of a thing, right? So this textbook also does the same thing, but I mean, this is actually quite confusing. So don't get confused by this. So that's why I suggest that you don't read this last section of that textbook, because it's actually really confusing. So again, I repeat, on the dielectric, there are no free charges. So every part of the dielectric is completely neutral. So what we have is just the electric dipole moments, molecular electric dipole moments distributed over the whole volume of the dielectric. And we know that the dipoles are charge neutral. And so therefore the whole dielectric is also charge neutral. Somehow these dipoles create an electric field, and we have to take that electric field into account too. Okay, so let me add one more thing in here. So that's the confusing part actually. So when I said about the polarization in here of that molecule, the polarized dipole moment, the dipole moment of that molecule, I said that the electric field E2 is the one that polarizes it. Not really, it is the one that starts it, but all the other molecules also produce an electric field, which also applies an electric field to that one. So I mean, this dipole is also affected by this induced electric field as well. So as a result, this dipole moment is actually proportional to this total electric field in here, right? So, I mean, there are these kind of issues that makes the problem really complicated. And to be able to solve this problem mathematically, you have to actually sort out these kind of complications, all right? That's one of the reasons why this problem is actually complicated. I mean, it's not just the vector sum of electric fields in different directions, but there are also some other issues in here which makes the problem really complicated. But in any case, math is complicated, but the physics is not. So just keep this in mind. Okay, let me stop here. And if you have any questions, then I'll take the questions in the, after I stop this.